Okay, let's continue this section. The next talk will be Eurica. She's going to talk about anisotropic PDEs, some results, and several problems. Thank you.
Thank you so much. Let me start just to thank the organizers, especially Kenny, for the invitation to be here. It's quite a pleasure to be in this beautiful place and hopefully to share with you something that I'm working with and you find it interesting as well. So I will be talking about anisotropic PDEs, meaning that, just to have the context. So we have this evolutionary situation, so we have a function that depends on time and space, and we are considering differential equations having space and time derivatives, and we are going to work on this nonlinear setting. So the most famous equations having this kind of property are the porous medium equations, so the first one here, saying that the diffusion happens by this expression here, u at the power m minus 1, and it happens independently on each space direction we are considering. If we are now considering that the problem that appears for having this nonlinearity is not related to the medium that we are working with, but with the fluid, let's say that we have a non-Newtonian fluid, what happens is that the diffusion now is given by this gradient of u, so the norm of it at the power p minus 2, meaning that the gradient of u is the set, is the vector of all partial derivatives regarding the space components of our point tx. So the green does not work here, so sorry. In these two cases, what we have is that regardless each space direction we are having, we are continuing always to have the same kind of diffusion. If we are saying that that is not the case, we can have two cases. One is called the pseudo-P-Laplacian, that is the one here, says the following. The diffusion now does not depend on the full gradient of u, but just on the specific I partial derivative of u regarding xi. So this is the major difference between this pseudo-P-Laplacian and the isotropic P-Laplacian. Okay? If we ask for something worse, we have the anisotropic case, meaning that in the case of the porous medium, it means that now the exponent is different in every single direction in space. In the case of the P-Laplacian, we get what happens for the orthotropic case, let's say the pseudo-P-Laplacian. So we just have the u of xi instead of the full gradient of u in space, but also we have the difficulty of having a different exponent pi in every direction in space. Okay, so this is the usual anisotropic P-Laplacian. And there are several people working on this for several years. Even in the elliptic case, meaning that we have stationary problems, so we don't have the time derivative of our function. It does not depend on time. And I'm just naming or quoting some of them, so it's not an extensive list of people working on this. So I will try to show you, by saying nothing much, let's be real, what I've been working with. So I started to work with this anisotropic equation that was a little bit different. So I got to know the work of Antonsev and Shmarev, and they said the following. When working with this Dirichlet problem, and we have this anisotropic setting, because now the exponent, as if this is the porous medium, but the exponent is no longer a constant. It depends on space and time. And they proved that for this Dirichlet problem, if this gamma is a bounded function bigger than -1, then they proved existence and uniqueness for the solution and several properties for the solutions. What they did not prove was regularity. Okay, and that was the topic of my PhD. So this was part of my PhD thesis several years ago, and that was precisely my point now, at that moment, was to show what one could say about regularity for the solutions of this kind of equations. And under the setting where we define what we mean by a local weak solution, and if you are familiar in this case of working with PDEs, it is quite striking the way that you say that you are working with a solution, because there are different definitions of solutions. So in this case, considering local weak solutions to be a bounded solution, it is not something that is quite not expected when trying to prove regularity. We always start with saying that we have a bounded function, so this is not something, but asking for some regularity assumptions, meaning that this assumption here for u allow us to say that this first integral and this one have a meaning here and are bounded. And the second regularity assumption on u allow us to say that this second integral here is also something that has a meaning. So what we were able to prove is that considering that we have, and we distinguish two cases, the degenerate case, meaning that the exponent is positive, bounded and positive, so the A2, and the second one, considering negative exponent, gamma, bounded negative, so it means that our equation is singular. And also we consider this regularity assumption on gamma, that was something new at this moment, because there's no extra imposition on gamma in order to prove existence and irregularity. And we were able to prove that under these assumptions, either for the degenerate case or to the singular case, the solution was Holder continuous if we started with a locally bounded solution, okay? But this A1 assumption, the assumption that gamma has to have this proper regularity, it seems too much. It was very demanding in the proof, so it was a technical assumption, and everyone, well, I don't know who everyone is, but several people that I was talking to said, okay, it is not a natural thing to ask for the solution. And some years ago, that thing was kept by the back of my mind. I was able to consider just the boundedness of gamma in the degenerate case and get the regularity assumption. So by assuming nothing about regularity on gamma, the proof of continuity was also available. The proof has to be a little bit different, but it was possible. But the same technique did not work for the singular case, so I could not avoid that in the singular setting. So a little bit further, I also work with the anisotropic porous medium. And in this case, I considered, so the exponents, mi's, I consider them to be positive and bounded. Okay, so this bar E stands for the maximum, and this bar here, under bar, stands for the minimum. And considering proper a notion for the weak solution, what I was able to prove is for the singular and the degenerate case you could have local boundedness, but I'm not allowing the mi's to have some mi's that brings the singularity and others that brings the degeneracy. So all of them should be greater than 1, and we are in this low diffusion range, or all of them should be less than 1, so the exponents would be negative when we are in the singular case or the fast diffusion. Okay. I don't know if you are quite familiar with the techniques related to this, but I'm just saying the topics that are major when proving the continuity, because this is the big issue and working on this. So what we want to do to prove continuity is to show that the oscillation goes to 0 as we are approaching the point. Okay? And by doing this, what we want to see is the following. Define a sequence of sets. Our sets will be cylinders because we have space and time. Okay? We are shrinking the cylinders to the point. As we are doing it, in each cylinder, we are considering an oscillation of the solution. So what we are saying is that as the cylinders are shrinking to the point, this oscillation is going to 0. And the way to do this is to, well, at least the way that I do it, is I go back to the technique presented by Di Giorgi in the 50s for elliptic case, that was extended for the parabolic case in this case of nonlinear setting by Di Benedetto, and I tried to use this kind of technique to show that we can have this reduction of the oscillations choosing proper cylinders. These proper cylinders are what we call this intrinsic scaling. So choose cylinders, so choose a dimension in space, choose a dimension in time, in order that your equation behaves well, and you can then do the procedure that is related to this reduction of the oscillation. And there are two major, at least at this point it was the case, two major important estimates. Energy estimates like Cacciopoli estimates and logarithmic estimates that are very technical. And once we get these bigger estimates, more or less everything goes well. I say more or less because there are, of course, things that we cannot avoid. Well, the thing that I did here, I did separately for the singular and the degenerate case, but along the proof, the constant will depend on this oscillation. So it will depend on the solution. So I could not present a modulus of continuity. I could say that it is Holder continuous, but I could not say how this Holder continuity goes. Recently, I went back to these anisotropic PDEs, and I started to work with Simone Ciani, that is currently at the University of Bologna, and with Igor Shripnik, that is from the Academy of Science of Ukraine. And we started to work with anisotropic P-Laplacian. And the anisotropic P-Laplacian asked us to work with different PIs. So we needed a different Sobolev spaces. This is not new now, okay? This is quite known at this moment. So we have this bold P that stands for the vector of all PIs. So when we ask for a function to be here, what we are saying is that it has to be integrable, and its gradient also has to be integrable. So the gradient meaning only the space derivatives, the vector of space derivatives, and each partial derivative has to be in the corresponding LPI. Okay, and well, it's something that we always have to have, is this kind of Sobolev embedding. And in this setting of anisotropic spaces, what is known, and it is available, is this estimate that says if you can relate this exponent q, as it is written here, where this p star represents the Sobolev exponent when considering p, being p the harmonic average given here, what we can have is a relation between this LQ norm of V and this L infinity LS and this LPI, but now not for the V, but for the V at the exponent alpha I, when we are asking these alpha I's to be non-negative. Okay. So once again, what do you mean by weak solution? Okay, set that kind of initial start point. What we could prove was that with this notion of local weak solution, we were able to prove Harnack type inequalities. And from that Harnack type inequalities, we could present how the solution decays. Well, how do I say that the solution decays? We are just working in the singular case, so all PIs are less than 2, between 1 and 2. And in those range, what was already known was that there was a time after which the solution is 0. So how is she getting down to 0? That is the estimate of the decay rate. That's one of the things. And we also got it for the anisotropic for the anisotropic porous medium equation. The same kind of results, more or less the same kind of techniques. To be real, or to be accurate, it was not for the prototype equations, but for a wider class of equations that is given here by this identity 1, where we are asking for these two operators, capital A and B, to satisfy proper structure conditions. So if this C here is 0, what we have is the prototype, more or less, because we can have something that is related with the prototype given by these two, let's say, elliptic condition and growth condition for the operator A. So what we got was these Harnack type estimates. Just in a few words, Harnack says that you can control the sup of a solution by its inf. Okay? These L1 estimates, that is called the integral form of Harnack estimates, that says that we are not saying that the inf of U is controlled, sorry, the sup is controlled by the inf of U, but the sup of the L1 norm of U in space is controlled by the inf in time of the L1 norm. That is why it is called a version of the Harnack, okay? And then another one that is quite common in the literature is to say that you can control the sup by the L1 norm of the solution. Having these two possibilities, we can then get the decay rate. Once you know that there's a time after which the solution goes to 0. That was known for the anisotropic P-Laplacian, but it was not known for the anisotropic porous medium, and we proved that T star exists. So that was the time after which the solution is 0. And we did it in two different geometries. Let's say the standard geometry, that you use the usual cube. So what we are saying is that in space what we have is a cube of radius, in this case rho, and this new intrinsic geometry that says that you are not working with such kind of cube, you have to do something in space that is related to anisotropy presented by the equation. Okay, so why to choose this kind of intrinsic? Are we getting something that is nastier just to show off, something like that? And it is, well, it could be. It was something that is always available for everyone. But it has a double meaning. Just to have homogeneous estimates is quite good. Homogeneous estimates meaning that the MIs or the PIs no longer appear. Somehow we can take them back to the geometry and they more or less disappear by the end of the estimate. Or we can have a bigger or wider setting where we go back to something that Barenblatt did so many years ago, and we look for this context of self-similar solutions. What does that mean? Consider three, well, not three, n plus 2 constants, positive constants, these m, li's, and t, and consider a function that depends on the other by the relation that is given here. Okay, so you put u over m, and then instead of having x, 1, x2, whatever, you are putting something, this L1, x1, okay? And then instead of having just the time t, put a capital T and see what happens. If you ask the two functions to be solutions, let's say to the prototype of the anisotropic porous medium equation, what we are saying is that we have the time derivative for u somehow related to the time derivative different times, right? For V, and since V satisfies the anisotropic porous medium, we have this, and then if we compute these derivatives regarding the Y's, what we have is something like this. So we get this extra. But we want U to satisfy the same equation. So this red expression here has to be 1. And then we get a relation between these constants that we introduced. And by saying this, if we are asking, let's say, to have the conservation of the mass, what we are saying is that this very simple cylinder, this Q1 here, so we have at the basis, we have the cube, and then we have the time interval 0, 1 for time. What we have is that we are transforming this Q1, if you are just taking what is given there, by this new one. So what we are saying is that in each I direction, we are considering different intervals, okay? If we are considering a different Li that comes from here just for a proper choice of this capital T, what we have is different things, but now we are having something different in space and something different in time. So these two geometries are possible, available, and there are several other more. And what we can say is that these kind of new geometries, they leave the energy estimates invariant. That is quite good. So both of them work. The first one says that if we consider small m's, then what we have is that all the space intervals are stretched, okay? But they do not preserve the volume of our cylinder. For the second one, we cannot say that all sub-intervals are stretched, because some of them are shrinking, some of them are getting bigger, but the volume is preserved, and that is something that we would like to have. So we choose the second geometry, and then for a particular choice of the A and the M appearing them, we worked with this kind of, let's say, calligraphic K of rho, saying that it depends on what happens in time. So this T here is fixed, okay, divided by this rho square. It is something that we would more or less expect it to have, because we are having these two derivatives in space for one derivative in time. And then this M appearing here is just the average. So some of the MIs are above, some of them are below the average, so this could be positive or negative, it depends. Okay, so what happened, and I'm more or less going to my point, is that if we are considering the intrinsic geometry, what is the price to be paid? Well, we have the possibility to say that we can have this L1 Harnack, so the soup is controlled by the inf of the L1 norm, okay? When having just rho, we are comparing to the 2 rho, and we are getting this extra term here. This is related to the fact that we are not working with homogeneous equation. So we have that capital B appearing, okay? And this is something that we have in the isotropic case, so it's quite good. So the geometry brings us to something that is not depending on the MIs. Everything here, so this lambda do not depend on the MIs, and this M, so it's the average, so it's a constant, right? It is not something that is changing in each direction. I have to say that if we are considering all MIs to be the same, we are getting what is known for the porous medium equation. So in this case, it is a good result. We are going back to something that is already known. If we are considering the standard geometry, what we have, so sorry for the green, at my computer it worked just fine. We have something that is simpler, as to say something about the kind of radius that we have to choose, but the price to be paid, okay, we have the soup of the L1 norm controlled by the influence of the L1 norm, but then we don't have something that is, let's say, I independent. We have to sum all of these. And what happens is, having something like this, there's a price to be paid when we are going to get the decay rate. So there's an extra effort when considering simpler geometry. So there's this payback. Choose something simpler, but then there's a price to be paid. If you choose something more, I would not say advanced, but more related to the problem, then it will be simpler. But, okay, it's not everything are good news. With this anisotropic geometry, what happens is that when we are getting this decay rate, when we are approaching the time for which the solution goes to zero, some of the sub-intervals, some of them are becoming quite big. So we are getting out of the cylinder. So at a certain moment, what we are saying is that near this extinction time, it's not that good, let's say. Okay, so just to finish my presentation, I'm just talking a little bit about what we are trying to do now. So what we are doing now is mix all of the two anisotropic equations. So this is a blend between the porous medium and the P Laplacian in the anisotropic setting. What we are trying to do is to prove several results, several regularity results. So I would say that this part is the several open problems, and there are so many other open that we are not addressing. So what we want to do is to do this expansion of positivity, meaning what? Expansion of positivity says this following. We are working on cylinders, right? So fix a time level, and consider the cube that is located at time level. If you know that the solution satisfies something on that cube, can you say that it satisfies something alike in a cylinder that is centered on the top of our cylinder? So you can use it in order to prove regularity. That's more or less the thing about expansion of positivity, what it means. So that is one of the things that we are working on. So I would say that this part is already done. Having this at hand, we can prove Holder continuity. We just have to see how, because this is the major tool in order to get Holder continuity. Our approach of getting this reduction of the oscillation in smaller and nested subcylinders. Another important thing is to have Harnack. And once you have Harnack, you can use it also to prove regularity results. Harnack type estimates are easier to obtain at Harnack, but we are trying to do this. We are almost done for a part of it. And then prove boundedness once again, and then get some expression for the subpotential lower bound of our solution. So this, I would say, this is a major project that have several things, but once we can have all of these, more or less we are saying the old story about regularity results related to these doubly nonlinear anisotropic equations. So thank you so much for your attention.
Thank you very much for your really clear talk. And do you have any questions, remarks, comments? So, okay.
So thank you, Eurica, for your presentation. In this list of ongoing projects, do you think it would be possible to consider a function in front of the...
On the right-hand side?
No, on the left-hand side, on the spatial derivatives. Can we have a function dependent on X with some properties accounting for different spatial scaling in the problem of porous media?
Yeah. I would say that once we have something, I'm going back, sorry. We can have something more general like this, but then we have to ask for the operators. So instead of considering this A to be that kind of prototype that I'm presenting there, we can ask for something, but then it has to satisfy proper structure assumptions in order to get the estimates that we need, because we will try to need to control what happens in space, and in order to have that, we need this kind of elasticity condition and growth condition. So we can ask for to have something more, but it cannot be anything. Okay.
So, okay, then we can talk perhaps because I would be interested in some kind of description in which we have very different spatial scales in this porous media problem.
Okay. So this anisotropic setting, precisely.
Perhaps.
Okay.
Thank you.
Any other questions?
Naive question, and if the situation goes wrong, does the solution explode? What happens?
Well, that is precisely what we mean by singular. We are allowing the solution the solution to explode. Oh well, no. No. We are allowing the diffusion to explode, because here the diffusion is given by this. So when we are in the singular setting, meaning that all mi's are less than 1, this exponent is negative. So at the points where u is 0, that we are allowing it to be 0, this goes, right? It explodes. But the solution, no, because our starting point is that the solution is locally bounded. Okay, we need that in order to control the oscillation.
Other questions or remarks? Okay, if not, let's thank Eurica again.
Thank you.